means of different classes. You guys agree?
Yes.
So let's take a look at this example. Okay. So red is one class. So again, a lot of red points over here. The mean happens to be this one. Okay, very similarly, a lot of blue points over here. Let's say the mean happens to be over here. Okay, so let's pretend we have two choices. To project it on these axes, and again, this is a two-dimensional data, right? Or to project all of these points on these axes. Which axis maximizes the difference between the means? The vertical or the horizontal? Horizontal, right? Because you can see vertical projection, the mean difference is only this much. Horizontal, it's high, right? But then what will happen if I have a data point over here, which is red class, and a data point over here, which is a blue class? If I project them over here, wouldn't they be very close to each other, hardly distinguishable? So that doesn't seem good. On the other hand, now let's go to over here. I have a data point, same example, to red class, blue class, and I project them over here. So is that a better choice? So what I'm trying to say is LDA, a single goal should not be the only criteria, because then it will fail in these cases, right? So basically what we do is, we still have this goal, but we divide it by the variance in the data of classes. In other words, we have to pay attention to the variance also, because if there's an overlap going on over here, then it's not a good projection. Okay, so anyway, now there's a little bit of a, okay, today I'm short on time, so let me at least give you the summary, then I'll come back and clarify the math further. But let me skip the main math so far and show you the procedure. Okay, so the procedure basically goes like this. We create what are called between class and within class matrices, okay, covariance matrices. So these are called scatter matrices. Okay, so take a look at this equation. Okay, I basically indicates the class. So if we are doing face recognition, we have, let's say, let's take a look at the AT&T example. We have 40 different persons, right? So there will be 40 of these matrices created. S0 through S39 or S1 through 40, whatever you want to think of it, right? X is one of the pictures or in vector form. So what does this look like? Doesn't this look like the covariance that we are creating?
Yeah, quite a bit, right? T is transpose, right? No.
Right, let's see, if even in PCA, if you recall, once we were creating the covariance matrix, it was basically XX transpose or X transpose times X. So, and we already had subtracted the mean from each one of these. So it is exactly like PCA, with the difference being PCA does this on the entire data set. What are we doing over here?
Class by class.
Class by class. Okay, so once we do class by class covariance matrix, then basically we create within class scatter matrix by adding all of these matrices. In this example, the author is assuming two classes, so it only is S1 plus S2, but in our case it will be S1 plus S2 plus S40. So once SW is computed, okay, that essentially is sort of an indicator of the means between, so anyway, to combine the two two goals that we mentioned earlier. We have to have one more matrix over here. So the other matrix, again, I'll go over the math next time, but today let me quickly show you, is called, okay, the next matrix we create is basically called the SB matrix. So between classes, which will take a look at the mean. Okay, so as you can see, this is basically doing mu. Again, this example is for two classes, mu1 minus mu2, mu1 minus mu2 transpose. So that will give us SB matrix. Okay. So again, what is mu1? The mean of the first class. Mu2 is the mean of the second class. Then once we have SB, in the previous matrix we called it was SW. Okay, so in the algorithm, like I said, compute SW, compute SB. Then basically we come up with an optimization function, which looks like this. Okay, and how do we solve it? Okay, we take the derivative, and I'll go over the math next time, but let me show you the final answer. So the final answer is, where did it go? Okay, so suppose, you know, as I mentioned, we know how to compute SW, like S1 plus S2 plus so on, right? This is the between class mean, the means, mu1 minus mu2 transpose mu1. For two class problem, it will be like this, right? For more than two classes, it becomes again the covariance matrix, which it becomes a covariance matrix of the means. I'll give you the detail in a second. But anyway, so as you can see, this is basically the covariance of each class. So we know how to compute this. So this is pretty easy. This is covariance of the means. So this is pretty easy. So then we create this matrix Sx by multiplying SW inverse times SB. And then as you can see from this, can we compute eigenvalues of this? Corresponding to these eigenvalues, can we compute eigenvectors? And then convert these to basis vectors and project any incoming onto this. And that will give us the optimal projection where the data between classes get separated. Okay, so let me quickly show you the pictures, and next time I'll go over the math so that you can easily see it. So let me show you. So the nice thing is they take you through a simple 2D example showing you each and every step over here, how the S1 is being computed, S2 is being computed. Anyway, so it's very easy to follow. I'll just show you the results. Okay, the example they give you, the first example they give is like a 2D case. So the projection will be onto a single dimension, right? So which is computed through the that eigenvalues, eigenvectors. Okay, so because this was a 2D example, we will have two eigenvalues once we assemble, and of course two eigenvectors. Okay, so each eigenvector corresponds to an eigenvalue, correct? So if we take a look at the projection for the smaller the eigenvector which corresponds to the smaller eigenvalue, then this is what that vector looks like. Okay, if we project it onto this, is this a good projection or a bad projection?
There's
bad,
It's bad. because it's-
right? Okay, because this was corresponding to the low eigenvalue.
Yeah,
Now on the next page,
the high one will be better.
this green one is the eigen corresponding to the high eigenvalue. And if we project all of our data over here, is it maximizing the class separation?
Yes.
Okay. So anyway, if you can at least try to go through the 2D example, try to get an idea of it, and within 1 or 2 days, I'll put together a nice summary of the coding part, so that, and like I said, our goal is by the time we are done with this course, I would like you to be very, very comfortable with the math, with the implementation for classical vision, modern vision, so that, you know, if you go anywhere for a job interview or later on in your professional field, you have if you have a good foundation, you can do anything later on, okay? All right, I'll stop here.